So if we're talking about small fields, the place that I'd like to start is the definition. What is a small field? What are we really talking about here? And the best definition that I've found is from the TRS 483 publication, and that defines small fields as having at least one of these three conditions: loss of lateral charge particle equilibrium on the beam axis, partial occlusion of the primary photon source, which changes the energy spectrum that you see from that photon source, or the size of your detector is similar to or large compared to your beam dimensions. Because a lot of our assumptions on cavity theory and things like that start to break down when the size of the detector approaches the size of the field that's being used. So from that starting point, now the question is, when we're in these conditions, in these small field conditions, how do the detectors impact your measurements? So the very first one is really, how big is your detector? What's the size? What's the shape of your detector? Because there is geometric volume averaging that occurs just because you're integrating a signal over a specific finite region. No detector in the world is a perfect point detector. There's always some spot size, some integration region that may be large enough to affect the profiles that you're measuring. So it's good to know, if you have an ionization chamber, what the spot size is of your chamber. And what I mean by spot size is really what's that full geometric region that's covered by the active region, and usually the cap as well, because that does impact the interactions of this chamber with radiation, as well as how much water is displaced. If you're measuring, you should be measuring water, but if you're measuring in water, how much water is being displaced by the physical dimensions of these detectors. It's very important with small fields that you are consistent and accurate with the positioning of your detector. When you're looking at a 10 millimeter field, a 1 millimeter offset can be a very massive difference in the dose that you're measuring. Where if you're in a 10 centimeter field, a 1 millimeter offset really doesn't affect things very much. The second way that your detectors affect the measurements that you're making is by changing the interaction of the radiation right there at the point of measurement. So you're perturbing your beam, changing that dose deposition by putting something in the field. You're altering that dose by replacing the water with your detector. So depending on the detector that you're using, for an ionization chamber, really it depends very much on how large that air cavity is. If it's a diode, the higher density of the diode affects the measurement. Some diodes have what's called compensation, built-in compensation. Often that's a low density region to try and balance out that high density. That's very good for the specific energy that it's made for, but it may not fully compensate for the difference in density at different energies. So it's good to have a full characterization of your diode to understand shielded versus unshielded, compensated versus uncompensated. Those factors all play into it. And for scintillators, there are the primary question with scintillators is whether this is water equivalent for the beam that I'm measuring. If it is, that makes those corrections a little bit nicer. If it's not, then we need to understand what the differences are. The third way that your detector can impact your measurements, particularly with scanning, is the signal level. So with a nice, highly precise calibrated electrometer, you can carefully choose the range that you're measuring in, appropriate to the detector that you have. Your water tank scanning electrometer may not have the full range and the full accuracy, particularly at low signals, that a standards level electrometer might have. So to be aware, with ion chambers, your signal is directly proportional to the air cavity, to the collecting volume. So your signal to noise ratio with ion chambers becomes more of a concern as that volume decreases and your signal decreases. Now you might be running into potentially more concerns with the cable, with the electrometer, electronic noise or background noise, making sure you're zeroing. All of those things play into the accuracy of your measurement. And definitely those small signals require an appropriately sensitive electrometer. So if you have, excuse me, a water tank that's really only designed for higher signal or optimized for the 0.125 cubic centimeter scanning chambers, it may not be as sensitive as it should be for extremely small ion chamber type measurements. For a diode, you do get a much larger signal usually than you do from the micro-ionization chambers. That is one of the advantages of scanning with diodes, because that puts them nicely into the range of signals that can be measured easily and accurately by your water tank electrometer. For something like the scintillator, you get a small signal level from the scintillator. That means you do have to slow down your scans in order to get accurate measurements. And I'll talk about that a little bit more later on here in this presentation. Signal to noise ratio, I mentioned a little bit with the ion chamber, but that's something also that can affect your measurements. If you have a leakage current or you have not given your electrometer a proper warm-up, that measured signal can change throughout the course of measurement just because of the difference in terms of electrometer warm-up, specifically the difference in the resistance of some of the components within that circuit as they change temperature. That can change the way the measurement is made. It is important to minimize your signal to noise ratio, both by choosing an appropriate detector for the electrometer that you have, but also choose the proper range in your electrometer for the detector that you're working with. Another way that detectors impact your measurements is just the accuracy of your detector. There are a lot of different characteristics of the detectors that can impact your accuracy depending on whether you are actively correcting for them or not. So for instance, energy dependence of a detector. Diodes are often low responders in the out of field portion of the scan, and so you can, if you only scan with diodes, you can underestimate that out of field dose, which if that translates into your treatment planning system, you might underestimate that large region of lower dose in your stereotactic patients. We talked about whether compensated diodes are good or bad. It really depends on the diode you're using and what it was designed for, how well you're using it compared to what it was intended to do. Corrections for energy dependence may be both depth and field size dependent. So if it's easy to ignore energy dependence by just making the excuse that all of these measurements are relative. I'm doing a PDD scan. It's all being normalized, so my energy dependence doesn't matter. But it does if the energy dependence is large enough that change in energy with depth, say for an electron scan, in particular, affects the response of the detector. So it is something that needs to be considered in the scanning world as well as the dose calibration world. Same thing with scatter conditions. If there's an energy dependence, low energy scatter or changes in the amount of low energy scatter can definitely affect the response of your detector. If you have any angular dependence on the detector, this generally doesn't come into play as much with scanning until people are tempted to turn something on its side or end on in order to try and minimize cross sections to decrease the volume averaging, and then you may introduce an angular dependence that you didn't think about beforehand. So it's best to use detectors in the orientation for which they were designed, and if you don't, be aware of the implications. Make sure that you verified that you're not causing any offset in your measurements, any additional dependencies that come from the fact that you're not using the detector in the orientation it was designed for. Some detectors also have dose rate or dose per pulse dependencies. This becomes a bigger question as there are more and more places looking at flash radiotherapy. Dose per pulse has gotten a lot of attention lately. But understanding your accelerator, understanding your detector, being aware of the dose rates that you're using, if they are within kind of the standard radiotherapy range, or if you're doing research that's pushing the boundaries on that, you should be aware that this may affect your scanning measurements as well. So that's a lot of problems to consider. That's a lot of complications to think about. The question at the end of the day is, what detector should I use? What can I pick that I can actually trust? And I would say, first of all, we have options for you. The A26 Exradin ion chamber is an excellent small field detector. We have the D1V scanning diode, and then, of course, the W2 simulation detector. But as with any detector that you find on the market, every one of these has both strengths and limitations. I like to be very open about that because I want you to do the best dosimetry that you can. So the best solution that you can have for small field dosimetry is a good combination of detectors, so that these strengths and limitations, or these strengths can complement each other so that we can get around some of those limitations. So in terms of the ion chambers, that A26 is the smallest ion chamber that we make. I take that back. It's not the smallest ion chamber that we make, but it is the smallest one that is made as ion chambers ought to be made. So it's all the same conducting plastic for the shell and the collector and the guard in order to make this chamber behave in the way that we expect our reference chambers to behave. We also designed it with a spherical spot size so that whichever orientation you have it, you're not changing the physical volume averaging for that orientation. The volume is slightly larger than the A16, which is our very smallest chamber, but that's because the A16 has a wire center electrode, and that was the reason we could make it smaller. In terms of design considerations, we were trying to make sure that we'd have a signal magnitude large enough that the scanning chambers or scanning electrometers could use this detector, but it needs to be robust and stable enough, of course, to be a standards level detector as well. So strengths of the A26, it is a reference class. It was designed as a reference class ion chamber. The spot size is independent of the orientation of the chamber, so you don't have to worry if you're scanning along the axis of the chamber versus the other direction. You don't have that elongation that a lot of the smaller chambers have. And it's a familiar technology for most physicists. We're very comfortable, working with ion chambers. It's something that we've been doing ever since we got into the field way back in, I won't say when. And it's something that we understand how to troubleshoot as well, which is important when you're looking at making sure that your results make sense. Limitations on the ion chamber really are the size. You can only make an ion chamber so small and expect to have good signal and good behavior off of it, and be able to manufacture it reasonably well, right, repeatably. You do get some small perturbations due to the fact that there's an air volume being introduced right there at the region where you're measuring, and so there are correction factors that come into play, as with any ion chamber. For the diode, the scanning diode that we have is called the D1V. There's also a horizontal version called the D1H. This was designed really to be in solid phantoms, so it's easier to machine. But the D1V provides the least amount of perturbation there in the water around the point of measurement. It was intended to be held vertically for scanning. It's the same diode inside. It's an unshielded diode. It has 1 millimeter diameter active area, so you have good fine resolution for scanning there. And there are, if you're looking at energy dependencies or field size dependent correction factors, there are publications that evaluated our diode, it's the green line here in this one, for small field measurements. Strengths of the diode, again, we're looking at well-established technology. Diodes have been used for quite some time, and most physicists are comfortable using them. The small spot size gives it a minimal volume averaging, so usually that's not a major concern until if you were looking at pencil beams, then yes, there's an issue there. There's not a lot of angular dependence, so if you're not perfectly flat in your alignment, you're not going to be affecting your scanning measurements. Limitations of the diode, again, as with any diode, is it's not water equivalent. These are higher density diodes, and therefore there are correction factors that have to be applied. Again, there are publications here in the green line. You can see it, our diode compared to some of the other detectors that are out there. There are correction factors. There are publications discussing this detector. The third detector option I want to talk about is the scintillator. This is the one that's not as familiar for most physicists. Our scintillator is an organic plastic that scintillates in the blue portion of the spectrum. Ionizing radiation interacting with this plastic creates visible light, which is transmitted down an optical transfer fiber. The signal is collected with some dedicated optics, turned into an electronic signal so that we can do some processing on it. And really that's where the measurement comes from. These plastic scintillators are water equivalent for megavoltage photons and electrons. Our optical transfer fiber is a PMMA fiber. It's been used in radiotherapy for years. The one detractant that makes scintillators a little bit more difficult to use is that you do generate Cherenkov light in this optical transfer fiber. So you have to correct for the presence of this additional visible light that shows up in your measurement. They also, being plastics, they degrade with dose, and so they're not the sort of thing that you can send into a calibration lab and get a fixed cal factor that's going to last you 3 years. You would cross-calibrate it in your clinic. Giving it a known dose can then give you output in terms of dose, but you would periodically recalibrate it as the material accumulates dose. The major advantage of the scintillator, as I mentioned, was water equivalence. That is validated here by the tables in TRS 483, where the W1 plastic scintillator has correction factors of unity for every single field size, for every single energy, for every single table. It shows up in TRS 483 correction factors or unity across the board. So this really validates our claim that yes, it is water equivalent. It's not showing this energy dependence based off of field size or based off of energy that many of the other small field detectors do. In order to correct for that Cherenkov signal, we use a 2-channel chromatic correction based on a publication by Matthew Guyot et al. From 2011. This is a representation of our scintillator signal. We have that blue scintillator. Cherenkov is this broad spectrum contamination. And so what we have you do is a couple of measurements where you keep the dose to the scintillator the same. So this portion of the spectrum doesn't change, but you change the amount of optical fiber in the field so that this Cherenkov spectrum shifts. So you have one measurement with less Cherenkov, one measurement with more Cherenkov. And we take the difference in the signal measured in this blue portion of the spectrum divided by the difference that's obtained in the green portion of the spectrum, and that gives us what we call a Cherenkov light ratio. That value is then used to correct subsequent measurements by taking the green channel signal multiplied by that correction factor and subtracting that from the blue signal. That effectively removes the Cherenkov signal from the blue signal channel. If you want to do a dose calibration with this system, dose calibration, it really just provides a unit conversion from the measured signal here into a dose. So it's just a multiplicative factor that is added onto this this equation. So you would give it a known dose, say 10 by 10 field at Dmax or at 5 centimeter depth. Give it a known dose and tell our system what the dose was, and that will create the conversion factor. So the W2 scintillator has, I should mention that the table in TRS 43 lists the W1, not the W2. The W2 was not on the market at the time that publication came out. The optical fiber for the W2 is identical to the W1. So all of those correction factors, which are affected by what material you're putting in the beam and how that material responds, there is no change from the W1 to the W2 on that. With the W2, we made a set of dedicated optics and electronics. It's called the Max SD for scintillation detector. And with this system, then we were able to make the optical fiber user replaceable. So it comes with both a 1x1 millimeter detector and a 1x3 millimeter detector for two reasons, actually. The 1x1 is what most people are looking for small field measurements because they want that high resolution. But the 1x3 gives you both a link back to all of the W1 publications that came out because it is exactly the same fiber, including the geometry, exactly the same fiber as used in the W1. But it also gives you 3 times the measurement signal for any particular measurement because of the 3 times the size of the scintillator itself. And so for times when you're not maybe measuring the smallest of your small fields, but you can get away with a slight bit of additional volume averaging and the additional signal makes your signal to noise a lot nicer, there are definitely places where people find that useful. So the Max SD can be used then for all of your characterization measurements and dose calibration, even point dose measurements can be done directly with this device. But it will also take an input signal, perform a fast Cherenkov correction for every 10 millisecond integration, and then convert that signal into an analog output. So send a current to, say, your water tank electrometer in order for the water tank electrometer to collect that signal and plot the scans in its own software. So what that looks like here is you would position the scintillator. We have an adapter sleeve that helps you get it increases the stem size so that this would fit in any standard chamber holder for anybody's water tank. It has been used, to my knowledge, with every vendor that I know of with their water tanks. This happens to be our DOSE 3D tank. So then the optical fiber is plugged into the back of the Max SD. Make sure with the Max SD that you've selected the proper Cherenkov correction file. But then there's a triax output from the Max SD into your water tank scanning electrometer, like our DOSE 3D water tank electrometer here. And from the point of view of your scanning tank, this looks like a diode. You're not applying bias to it, but when the beam's on, the water tank electrometer receives a signal. It is a low signal here, so we do apply a 25 times gain on the output to the water tank electrometer so that it falls in a good region signal-wise for most scanning electrometers. But you do also need to scan fairly slowly because it's a low signal device. We recommend about a 1 second measurement at each point, which adds up a bit if you were to measure small or large fields with it, but that's not what it's intended for, right? It's intended for small fields. And trust me, it's really worth the extra time to make sure that you have data that you trust the first time around that doesn't need a lot of manipulation and correction. So as I've done with the others, I've got strengths and limitations. Strengths for the W2 is really that water equivalence for megavoltage photons and electrons as validated by all those KQ values of unity. There isn't a correction factor required for beam perturbation energy dependence based on the field size or changes in energy for megavoltage photons. They don't show dose rate or energy dependencies. There's a negligible temperature dependence if you were to calibrate, say, at room temperature and then try and measure at body temperature. You might have to correct for that. But for general QA measurements at room temperature, there's no need to correct for temperature dependence. It's about 0.1% per degree Celsius. They can be made very small. We also make long fibers, so this can be used in MR Linacs. The Max SD needs to stay outside the 5 Gauss line, but nothing in the detector itself is ferrous, so it can be used, has been successfully used in various MR Linacs as well. Limitations of the W2 are that you do have to recalibrate it occasionally as that plastic accumulates dose. The optical signal measurements actually are somewhat non-intuitive to many users. We're used to ion chambers, we're used to diodes. We feel like we're a little bit out of our depth when we suddenly step into optics. And so it's something that you do have to take a little time to make sure you familiarize yourself with it, use it for a while, get used to it, and get over that learning curve. So that is a bit of a limitation. And the low signal to noise, the low signal of the detector itself means that your scans are a little bit slower. You do come up with some good scans from it, though. This is from one of the early W2 publications from Paulina Galavis, where she was comparing the W2 scanning measurements with a film measurement. This is for a 1 cm field. So with that, I think I've taken up almost my full half hour of your time. Are there any questions? Thank you so much for your attention, of course, first of all. But if you have any questions, please feel free to enter them. I'm happy to stick around and answer questions. If you want additional information on any of these detectors or on our 3D water tank system, 1D water tank system, any of that, for any of these small field scanning measurements, please visit our website. Don't hesitate to reach out to us as well. There is one. What is the field size recommended for the CLR calibration? There are a couple different methods you can use with the W2. So let me go back in my slides here just a little bit. With the water tank, with the W2, we send this small bracket. It'll fit within a 10 by 10 field that would span around this entire section of the bracket. You don't have to have the tip of the fiber centered for the CLR measurement as long as it's repeatable in the field. So putting a 10 by 10 field around it this way, doing minimum fiber configuration measurement with the fiber coming straight out, and then what we call maximum fiber configuration with the fiber wrapped around. You can do that in a 10 by 10 field. You can also use what we call the rectangular field method, where you might use a 2 centimeter wide and say 20 centimeter long field, and then rotate your collimator by 90 degrees. The key really, if you're doing a rectangular measurement, is that your short dimension needs to be wide enough that you have that you're not changing the dose to the scintillator if you're knowing the limitations of the walkout of your collimator, and that potentially highly peaked field profile. You want to make sure that the dose to the scintillator remains the same. You also need a big enough difference between the minimum fiber measurement and the maximum fiber measurement to have a good signal to noise ratio on the change in signal from the Cherenkov. So you do need a significant enough change in that signal in order to measure it cleanly. The third method you can do is that we have a calibration slab that we designed for the W1. That is an optional add-on to the W2 purchase, but that is a larger flat virtual water slab with a channel milled out for the straight out configuration and a channel milled out for the curved around maximum fiber configuration. And that measurement would be done in a 30 by 30 field. Then there are also markings for the 10 by 10 field calibration if you wanted to calibrate that way. So there are some options for field sizes for the CLR calibration, depending if you want to make your measurement this way set up in the water tank. If you're happy with the vertical plug that we have for this one that would set this up in the water tank, or if you would prefer to do it in a solid phantom. We do not have data for kilovoltage energies, so I can't tell you just how non-water equivalent it is. I do know that there are some materials in the scintillator that cause some, I think it's fluorescence at those kilovoltage energies, along with the fact that the signal is very low. So that's another limitation if you were to try and take the W2 down to kilovoltage energies. There's a question from Maria about how when the W2 scintillator should be recalibrated. The decrease in signal is about 2% decrease in signal for every 1,000 gray that the fibers receive. And it's a little more pronounced if you're doing slightly larger fields than you would see if you were only doing below 2 cm fields, for instance. But we recommend recalibrating at least every 1,000 gray. And depending on your level of use of the detector, that may be monthly, that may be every 6 months, or if you're calibrating a new Linac every weekend, it's probably going to be every weekend, right? So it depends on how heavily you're using it. Is there a limitation to the dose rate for the plastic and the W2? There are some investigations underway right now on some of that. I will say that this device was designed in the pre-flash era, and so the electronics were designed for handling very small signals, and extremely high doses create higher signals, and therefore the electronics will ultimately reach a saturation point. Exactly where that is and how that's defined and how we're going to handle that, keep your eyes on the scientific publications. We'll try and have something out that I can talk about before too long. Let's see. From Ying again, can we use the CLR of one energy for another energy? Yes, you certainly can. If you want the highest accuracy, it's often best to have a CLR specific to the energies that you're using. It's mainly because the scatter actually affects the measurement at the max SD. Usually you want that to be at least 1 meter away from the field. But in terms of the CLR, the actual differences between energies is so minimal that one CLR can be used for all energies. Longevity of the scintillating fiber and signs for need of replacement of the scintillation fiber. Generally, I have people watch the overall signal level as well as the CLR, and once that decreases below about 80% of what it was originally, I would recommend looking at updating your fiber. So ideally, that would last you 3 to 5 years or so. But I've also had people step on the fiber. I've had them get kinked and broken because grad student wasn't careful with it. So there's a reason that we make replacement fibers. It's actually quite easy to get one of those to you. So excellent questions. I love the engagement. Thank you so much. Any other questions from anyone? Please feel free to stick around and ask them. Otherwise, I'll close the webinar here in just a minute or two.